Should we do it?
So let's continue, and please welcome the container rockstar Liz Rice for this amazing talk, Containers from Scratch.
That's on. Got my mic on. Thank you so much for being here when I gather there's some kind of football thing. Thank you for being here. I thought there'd be like 2 people and everybody would be, you'll all be watching your phones, right, for the score. Okay, so I'm going to do the show of hands thing again. How many of you are using containers? Put your hands up. And keep your hand up if you are totally confident that you know what a container really is. Yeah. I totally relate to that. So I saw a talk kind of like this, probably well over 2 years ago now, by a chap called Julian Friedman from IBM. And this talk is very inspired by what he did. And essentially, we want to see what a container is by building one. Containers are really, they're Linux processes, and they use some constructs, namespaces, chroot, and C groups that we'll go through to containerize them. And we'll see how this is done. What better way of seeing how it's done than by creating one in a few lines of code. I'm going to do it in Golang. Have we got any Golang programmers here? Yep, a few of you. Good. You can be my peer reviewers and let me know when I've gone wrong. Okay, so before we actually start coding, let's talk about what it is that I'm trying to replicate. So, standard way of running an image, Docker run the image. So, if, for example, I were to do Docker run, ignore the flags, and maybe I would say something like Ubuntu, which would be my image name, and I'd say I want to run a process like bash. And I've created a container. It's actually given me a container ID, and that's also the host name for that container. And if I try to look at the processes in that container, well, they start from 1, and there aren't very many of them. Whereas if I'm on the host machine, this is the same machine, there's a load of other processes happening. So from inside the container, I have a restricted view. I can only see a subset of those processes. However, just to kind of demonstrate, if I run a process inside a container, and I look for that from the perspective of the host, I can see that. So the process inside my container is visible from the host, but host processes aren't visible from the container. And that's happening because of a thing called namespacing. So namespacing restricts what processes inside the container can actually see. And there are about half a dozen of these different namespaces, and we're going to work through a few of them. And we create them using system calls to basically say, when I create this process, I want it created in a namespace so it can only see this subset of what the whole host can see. So let's kill off this container and start writing our own. So I've got the very, very beginnings of a program here. Now remember, we're going to do, or what we're trying to replicate is Docker run, and maybe there would be an image name, and we could pass in some command, and maybe even some arguments to that command. And it would run that command inside the container. In order to build and run my program, I'm going to do go run, and then the name of this file, which is main.go. That is going to be the equivalent of Docker. That's running my executable that I'm going to build. I'm going to use a command here. I'm going to say we have to specify the word run. That will become clear soon. I'm not going to have an image. That will also become clear soon. But I am going to say maybe I'm going to pass in a command and some arguments. So I'm going to need a main function. And the first thing I'm going to do is look at the arguments we've got. And argument 0 is this go run main.go. That gets sort of turned into an executable name. Argument 1 is this command I want to run. I've called it run. So if we get run, we're going to have a function called run. And if anything else happens, we are going to fall over in a big heap and die and be very sad. Okay, and I'm going to need a run function. And let's start with a bit of debugging. I will just say what I was asked to run is whatever the other arguments. So that's arguments 2 and onwards. That's our command and any parameters that were passed in. Okay, so I save that. My editor magically does add some imports. And I can do go run, main.go, run, and let's say I want to do something really simple. It's not going to do it yet, but if I say hello Paris. Okay. So my debug line says I'm going to try to run the command echo hello Paris. Not really doing very much yet, is it? So we need to actually fork a process that's going to run, I've got a sign saying it's not very bright. I wonder if I think this might be the highest contrast color scheme I've got, unfortunately. How about, can people see that? Anybody at the back struggling? I can go bigger. Shall I go bigger? Are you happy? Okay, cool. Right. So I want to fork a process and run whatever command I've been asked to run. And I can do this in Go by setting up a structure. So I want to run argument 2, that's the command, and maybe pass in some parameters 3 and onwards. That doesn't actually run my command yet. I have to call this method run. What this CMD structure is actually it's a structure that describes what I want to run. I also have to set up stood in, stood out, and stdr, because otherwise we can't see what's going on. And here I get to use multi-cursors. Ooh, look at that. This is VS Code, by the way, and I think it's great. Okay, so that should set up my structure that says what I want to run, and it should actually create a process and run that command. So let's give that a try. And it did it. It told us it was going to echo hello Paris, and it actually did it. So I've been able to create a process and run some arbitrary command. I could run a shell, like we did inside the real container. And you can't really tell, but I am running bash. There it is. There's my go, and there's my bash. There's my main. If I do exit, it's kind of hard to tell that I'm inside another shell. Now let's try to containerize that process a little bit. So I'm going to do that by creating a namespace. And the first namespace I'm going to do is, it's called the Unix time-sharing system, which sounds really, really fancy. But actually, the only interesting thing inside that namespace is the host name. So what we're going to be able to do is change the host name inside my containerized process independently from the host's host name. And I do this by setting up or sending in some system call proc attributes. That needs to be a pointer. Sysproc attributes. And I say, when you clone the new process, I'll spell it right in a minute. I would like you to clone a new Unix time sharing system. Okay. So I'll build it and run it again. And we're inside my container. If I look at the host name at the moment, it's still got the original host name. But I could change that to container, let's say. And that's changed. But on my host, this is the same machine, I haven't affected the host name for the real host. So I've been able to isolate the host name inside my container. Okay? Now, it's pretty hard to tell whether or not I'm inside my container or not, other than by running PS and seeing how many processes I've got. And what would be really nice is if I could get the command prompt to change here. So if I could get this to say container when I'm inside my container. And, well, I could set the host name by doing something like syscall set host name. And for some reason, it needs to be a slice of bytes. But there is a problem. If I call that here, you remember I said that it's not until I do this run function that my new process gets created. And it's not until my new process gets created that I have a new namespace. So if I try to set the host name before I've done that, I'm still setting the host name on my whole machine. And if I do it sort of after I've run, if I do it there, that's no good to me either, because this run doesn't complete until it's finished executing this process that we've forked. So I'm going to get around this by basically doing this twice. So we're going to take a copy of that function. We're going to call the second one child, just our child. Right. And the second time we create it, or the second time we call this, we're not going to create a new namespace, but we are going to set the host name. And we're going to say, if we're given child as the command name, we're going to call child. And the first time through, rather than executing the arbitrary command we've been given, we're going to run this program again. And we can do that by calling proc self exe. Now, we'll look at the proc directory in a moment, but basically this is a link to the currently running executable. So I'm going to pass that in, and then I want to say, instead of run, I want to say child, and I want to pass in all the arguments to and on. But because this is Go, I have to do a little bit of sort of syntax. I have to say this is a list of strings, and I'm going to append arguments to and beyond. Right. So what I've done, we're going to come in here. We're going to call the first time. We're going to call it with run. That is going to create a process with a new namespace, and inside that process, it's going to run this program again, but substituting the word child instead of the word run. Don't want that there. And then the second time around, it's going to be calling child. That's going to come in here, set the host name, and then execute whatever our arbitrary command is. Okay? So, let's see what happens. Looks pretty good. So 2 things happened. First of all, we saw the logging happen twice, which is good. And secondly, there is the host name changed in the prompt, which you could do because the host name was changed before we ran bash and before bash ran its profile stuff to figure out what the host name was. So let's just confirm. Host name inside the container is container, and it hasn't changed the host name for the host. For the host. So we've started to get something that looks a little bit like a container. But you remember we looked at the running processes earlier in my Docker container. It's not behaving that way in my new container that I've built. I want to see processes that start at 1, and I only want to see the processes inside my container. And there is another one of these namespaces called clone new process ID, new PID. So if I do that, I'm saying in my new process that I create, I want an independent view. I want a restricted view, a namespace for these processes. Let's also log out what the process ID is for these commands. So in run and also in child. Okay, so that should get the process ID, the current process ID. So let's run that. Looking pretty promising there. We can see a process ID 1. So when we called the run function, it was running in the context of some high-numbered process, and then it created a new process inside the namespace for processes. But that is not what I'm hoping for. I'm hoping for PS to show me processes beginning with 1, and I'm not expecting to see the processes from the rest of the host. And it turns out that when you run PS, it doesn't actually magically find the set of processes somehow. It finds them from, let's do this on the host, from the /proc directory. Inside here, there's a directory for every currently running process. We could, for example, let's say we take that this bash 1458586 and 14586. I need to look at /proc. And that's going to tell me all sorts of interesting information about that currently running process. PS is looking at /proc and using that to tell it what processes are currently running on the machine. And for my container to only see the containerized processes, it needs its own version of /proc. And at the moment, inside my container, /proc is the same. So what I'm going to do is change the root. So I mentioned before, chroot is one of the things that kind of builds a container. I happen to have a copy of an Ubuntu file system sitting on my host, handily. And inside that, I've marked a file here called root for container. In the root on my host, I've got something marked as root for host. And right now, if I look at root inside my container, well, root, it's the same as root on the host. We can see root for host there. I'm going to give this container its own kind of version of the file system by pointing it at that Ubuntu file system here. So I can do that by chroot to vagrant Ubuntu FS. I think that's right. We'll quit here and run that again. And we've got this unreachable. And it turns out that when you do chroot, your current location in the file system actually ends up being undefined. So we'll quit out of that and we'll set it explicitly by changing directory to root. So run that again. Okay, it's not complaining about things being unreachable anymore. And there, inside my root directory, is the root for container marker that I showed. So we have made it so that the container can only see that directory and sort of beneath it in the hierarchy. It can't go any further up the hierarchy. It can only see a subset of the file system now because we've changed the root with chroot. This is pretty much what happens with a container image. I haven't done any sort of packing and unpacking, but when you pull a container image and, well, then you run a container based on a container image, it unpacks that image somewhere on your file system and chroots into that so that your container only sees that file system. And the end result is something very like this, where it's got something that looks like a whole file system, but only from its own perspective. So one of the directories I've got here is proc. And we needed proc so that we could run PS. Who thinks that PS is going to work now? Anybody think that's going to give me what I want? Yeah. We're pretty close. So it tells us what we need to do. Now, proc, it looks like an ordinary directory, but it's actually something called a pseudo file system. And that's a way for the kernel to communicate information to user space and vice versa through the medium of something that looks like directories and files. So we need to do this mount to say /proc is one of these proc type pseudo file systems that you can use to get process information. And so all we need to do is mount proc. Very important that I get these in the right order. There we go. And yeah, and I want to tidy up after myself, otherwise these start to sort of clutter things up. So I will unmount proc after I've finished. Oh, missing a comma. Okay. So, what do you reckon? Think it's going to work? It works! Hooray! Woohoo! So we can only see those processes inside my container, and they start from the low numbers that we were hoping for, which is great. Now, I've just done mount, and we can see that inside the container. There's my pseudo file system proc. And if I do mount on the host, there's actually a load of them. So let's just look at, let's grep for the ones that relate to proc. And we can see that /proc that we've just mounted inside the container, and it looks like it's mounted at Vagrant Ubuntu FS, because that's where it is from the perspective of the host in the whole file system. Now, if you imagine if you have lots and lots of containers, it might be a bit annoying to have them show all the mounts, or have their mounts showing up in mount on the host. And there is another namespace that we can use to prevent that happening. Now, this one is called clone new NS for namespace. Apparently, this was the first, mounts were the first thing to be namespaced, or the first namespace that had support added for it in the kernel. And I guess at the time they thought, yeah, namespace, that's, what else are we ever going to want to namespace? So they called it NS. Perhaps mount would have been a better name. Oh, there's one other thing I need to do. Now, this is kind of a bit arcane, but by default, mounts get propagated to, they sort of automatically get shared. And we need to explicitly say, I don't want to share the mount points that I create in this new mount namespace. So if I run that this time, and I can still see the mount inside my container, but now if I look for it from the host perspective, I don't see it anymore. That said, let's just do this sleep trick, and we can find the process ID of that from the host perspective, because just like in a real container, everything running inside my container is still visible from the host. It's still just another Linux process from the host perspective. And I can look at that process inside our friend /proc, 19713. If I look at root is quite nice to look at. Oops. We can see that that's telling us that we did the chroot to Ubuntu FS. And we can also have a look at the mount points. And so we can see we still have access from the host to seeing the mounts that are inside the container. So as root on the host, you can pretty much see everything that's happening inside a container. It's just that the container can't see what's happening elsewhere on the host. It's only got this very restricted view. Okay, so we looked at the first 3 of those 6 namespaces. You can kind of imagine how you can also isolate the networking stack, user IDs, even IPCs to prevent inter-process communications between different containers. They all kind of work in the same sort of a way. The final component that goes into making something that we call a container is C groups, short for control groups. And this is about restricting the resources that the container can use. So namespaces are about restricting what it can see. This is about restricting the memory or the CPU and so on that it can use. And this is using another one of these pseudo file systems. And we'll take a look. Wrong way, this way. So they're typically in sysfs C group. And we have directories for each of the different types of C group. And say, for example, we want to look in memory. And there are tons of different parameters in here. We can write into these files to set parameters, and we can read out of them to sort of read current status. But we could, for example, look at memory limit in bytes. And that's a very, very large amount of memory. That's probably all the memory on my virtual machine. So that's basically saying, by default, you can use as much memory as you like. Now, I don't know if you spotted, there's a directory there called Docker. And if you want to create a new C group, it's kind of hierarchical. And this is Docker creating its own C group. So let's see what happens. There's the whole set of parameters again inside that C group. But let's see what happens if we do another sort of Docker run like we did before. We'll run a shell again. Okay. Now, if I look in this directory, it's created a directory with the same identity as the container. And inside that, what is it, 20 something? Oh, Docker 20 something. We've got yet again another set of all these parameters, and we could look at the limit in bytes again, limit in bytes, and that container is not restricted at all. It's got access to 92 gazillion bytes or something. Now let's see what happens if we limit the memory. So let's say we limit it to 10 meg. We've got a different container ID, want to do this in the host. The previous container, or the previous directory has gone away, but we've got a new directory for 8.2 something. So 8.2 something, memory limit in bytes. And that is basically 10 meg. So Docker has told the kernel that we want to limit this container to having 10 megabytes of memory by writing this value into this file. It's created a C group specifically for this container. Okay, there are lots of different things that you can isolate through, or that you can limit through C groups. Another one that's kind of nice is PIDs. So this is the number of processes that are allowed to exist in the control group. So we can basically create a control group, put a process in it, and then it can only create up to that limit of, or there can only be up to that limit of processes. New processes automatically inherit the C groups of their parent. So I've got a bit of code that I've written previously to make things quicker. Here we go. So this is going to create a C group. We're in sysfs C group. I'm going to make sure we can go into the PIDs directory. Inside there, I'm going to create a C group called Liz. And I'm going to write into a file called PIDs max. That's the name of the file. That's the maximum number that I'm going to allow. And I'm going to say we can only have 20 processes. And then the interesting bit, or the other interesting bit, is that we're going to say, take the current process ID and write that into a file called cgroup procs, and that's the list of processes that have been assigned to this C group. Oops, I need to remember to actually call that function. Okay, so that should create a C group with my current process in it that can only have 20 processes. So, run main.go, run. Let's run a shell again. So now if we look in the PIDs directory, we can see it has created a Liz directory. We could go into that and have a look. Let's do that again. And if we check that the PIDs max file, okay, that's written 20 in there as we hope. We can see how many processes there currently are. It's actually saying 5. That's going to be to do with the threads that Go automatically creates. And we could also do the sleep trick again. And we find the ID of that, 20266. And if we look at the C group procs, 20266 is one of the processes that has been included in that C group. And that gives me some confidence that I have got this container running with a limit of the number of processes it creates, which is a good thing because I'm now going to run one of these. Bit of a sharp intake of breath, so I'm guessing a few people know what this is. Who knows what this is? It's a fork bomb. Right, so if you haven't seen one of those before, let's kill this sleep. What we're doing is we're defining it's a bash, bit of bash. We're defining a function called colon. And inside that function, we call colon, and we pipe the results into colon, which we run in the background. So that is going to continually just keep trying to fork as many processes as it possibly can. And then all we need to do is invoke that function. Don't do this at home. Okay. So that is trying its best to create as many processes as it possibly can. It's actually failing pretty quickly because it's not allowed to. The C group is preventing it from doing so. If I look in, let's look at the current processes. We have got 20, hopefully you can see that okay. We have got 20 processes running within that C group and no more. We can look at the set of processes, and there's a whole bunch of basically defunct processes, but we've been able to contain that attack. If that was a hacker setting off a fork bomb inside a container, by using the C group, we have limited its effect. And if I hadn't had that C group, then we probably wouldn't be able to do very much on the host machine because it would have eaten all the resources, and we just wouldn't be able to do anything. So, we've basically been able to create a container. We've been able to use namespaces to limit what it can see, so we can do things like PS and make it behave like a container, and do things like the host name. We've given it essentially the equivalent of its own file system. It's kind of like a container image by using chroot. And we've been able to limit the resources by using C groups. And actually, let's just check how many lines of code that was. 77 lines of code. It's not too bad. I think, I don't know what Docker's current valuation is, but for 77 lines of code, it's not bad. Couple of URLs for you there. If you want to kind of try that again, that code that I've written, or something very, very similar to it, is at that first URL, containers from scratch. And I'm also reiterating microscanner that I mentioned when I spoke this morning. Vulnerability scanning for your containers, and it's free to use, so why not? I think with that, unless everybody wants to just rush off and watch the football, we have time for a few questions. Yeah? Okay. Thank you very much. Merci beaucoup.
Thank you so much, Liz. So we have 10 minutes for questions, so do not hesitate.
Hi, thanks for the talk. Quick question. What do you think France's chances are against Denmark exactly?
That's a really good question. Unfortunately, pretty much everything I know about football is that there's a round thing. Yeah. I don't know. France, Denmark, they're both lovely countries. What can I say?
I do have a serious question, though, if I may. So you walked through a couple of interesting elements here, and that was super fun to kind of dive into the internals. My question is, how realistic is it, I guess, to build your own Docker, right? Like if that's something you're thinking, okay, I want to go ahead and actually build Docker, like the thing that exists today.
Right.
Is it really that simple, or?
Yeah.
I mean,
there is a reason why we didn't do the other three namespaces, because they do get a little bit more involved. So, for example, creating the network namespace, yeah, simple, just pass in another flag. But then actually you have to create a whole load of network interfaces and wire them all up, and it, it can be done, but it takes some typing. Why would you want to write your own rather than use somebody else's? Somebody else's that's actually been tested. This is not production quality code, people. There's no testing. Could you do it yourself? Yeah, you could. Would it be? It wouldn't be my advice. I mean, maybe I have heard people say they've got some specific use case where they wanted to use namespacing for some specific reason, so they've done it themselves, but it's pretty unusual. Yeah.
We have another question.
Yes, we've seen this running on a Linux system, but Docker is running also on Mac, even other systems. Docker is really bound to the kernel. How does it work with Docker running on another system?
Okay. So I'm really glad you said Mac and not Windows, because I know only slightly more about Windows than I know about football. But I do know a little bit more about it working on Mac. So Mac is very much like, it's a Linuxy, Unixy type operating system. The way they've implemented Docker for Mac is actually to use Linux Kit to run a virtual machine. So Linux Kit lets you run a sort of much cut down version of an operating system. And while that has lots of advantages in terms of it being lightweight and fast and efficient, it's also a little bit painful if you try. I did try to do this once, sort of SSH into the Linux Kit virtual machine and look at the Docker containers, and it's possible, but it's kind of complicated. The general gist of it is the same. You are creating namespaces in exactly the same kind of a way. Another reason to not try to do it is Golang, or if you try to run my code, Golang is lovely and lets you cross-compile for different platforms. All these things like the clone flags are only implemented for Linux, and I think maybe some Unix. They're not implemented for Mac. So this code wouldn't even compile for Mac.
First of all, thank you for the presentation. Maybe this question is a bit out of scope with what you presented, but never know. The common joke that I hear outside is that, Docker is not secure for whatever reason. Do you know more about this joke in particular? Why is it considered not secure? Because from what you've shown, it seems like it's pretty common and pretty standard with Linux. And second question, I've seen that there are at least tries of other companies building container runtimes, such as Rocket and this kind of stuff. Also, maybe out of scope, but do you know how it differs from Docker?
Yeah, okay. So answering that second part first, one of the main differences in the different kind of container implementations is to do with kind of what's creating those processes. So for Docker, you've got the Docker daemon, which kind of acts as a parent for all of these processes. And also, it's like the sort of central hub for every Docker command. And there are arguments to say, actually, we want to separate out the runtime from all the things like building and, image management. So one of the main differences between Docker and something like Rocket will be the existence or not existence of the daemon. For Kubernetes, we basically see, I guess, two kind of main implementations. So there's the kind of containerd, which is Docker's kind of Docker contributed containerd to the CNCF. So it's a completely open source, but it kind of originally came from Docker runtime. And then there's also another one called Cryo that, if I recall, came from Red Hat. And those both sort of play nicely with Kubernetes. And then there's also things that like Kata containers, which look like containers from Kubernetes perspective, but they're actually more strongly isolated than this. So they're actually more like, well, they are VMs. You're actually running your container processes inside VMs. And that kind of plays to the question about its security. Containers, in the traditional way that Docker's worked and what I've just shown you, they're isolated in user space, but they all share the same kernel. So if there is a kernel exploit, it may potentially be possible to kind of escape from one container into another in a way that would be harder if you didn't share the kernel. And for that reason, some people will consider VMs to be, well, I mean, VMs are, they are more isolated, so maybe a better security solution. Nobody in security ever talks about things being secure. They just talk about more or less secure or risk. And things like. And a lot of the time it will depend on what your application is, what the risk is. If you trust all the applications that are running on your host, you know, or if you vetted them carefully, then normal container isolation may well be sufficient level of isolation, and it's kind of nice and fast and efficient. It's much faster than having VM isolation. If you don't trust all the different workloads that you're running, you probably want to have something more like VMs.
And just one last question. No, okay. Cool.
Oh.
So, thank you so much.
Thank you very much.